Inside an electric vehicle, there's no fuel combustion, no engine explosions, and no exhaust emission system. So, what's actually turning the wheels? Because once you see what's happening beneath the surface, you'll realize this isn't just a different car, it's a completely different system. At a high level, an electric vehicle is built around three core systems: a high voltage battery pack, one or more electric motors, and power electronics that control energy flow. Supporting these are essential subsystems like a thermal management system to regulate temperature, typically a single speed reduction gearbox to transfer motion to the wheels, and an onboard charger to manage incoming electricity. No combustion engine, no fuel system, everything revolves around controlled electrical energy, but storing energy is only part of the story. The real question is how that energy becomes precise, controlled motion. The battery. The battery pack is the vehicle's energy source. Most modern EVs use lithium ion batteries made up of thousands of individual cells organized into modules. The battery stores direct current, DC, electricity, but in most EVs, that power isn't used directly by the motor because before that energy can move the car, it has to be converted instantly and precisely. Between the battery and the motor sits a key component, the inverter. The battery supplies DC power. In most EVs, the inverter converts that into alternating current, AC, for the motor. Then, the motor takes over. How the motor works: electric current flows through coils inside the motor. This creates a rotating magnetic field. That field produces mechanical rotation, no combustion, no fuel burning, just electromagnetic force converting electrical energy into motion. And this is where EVs gain a major advantage: how efficiently that energy is used. Electric motors are highly efficient, typically around 85% to 95% efficient at converting electrical energy into motion. By comparison, gasoline engines often convert only about 20% to 30% of fuel energy into motion. The rest is mostly lost as heat. Another key difference: electric motors can deliver maximum torque from zero speed. That's why acceleration feels immediate. No gear shifts, no delay. But here's where things get even more interesting. EVs don't just use energy efficiently, they can recover some of it. When you slow down in an EV, the system can reverse the motor's role. Instead of consuming electricity, the motor acts as a generator. The vehicle's motion drives the motor. The motor generates electrical energy. That energy is sent back into the battery. This is called regenerative braking. It doesn't recover all the energy, but it improves overall efficiency and can help extend range, especially in stop and go driving. And none of this works without constant real time control. EVs rely on advanced control systems to coordinate everything: managing how much power flows from the battery, controlling motor speed and torque, regulating energy recovery during braking, maintaining battery temperature within safe limits. These systems make continuous adjustments in milliseconds to optimize performance, efficiency, and safety. And finally, every system depends on one thing: how energy gets back in. Charging energy in. Charging an EV means supplying electrical energy back into the battery. There are three main approaches: AC charging, alternating current, common for homes and standard chargers. The vehicle's onboard charger converts AC into DC faster. AC charging, higher power wall units for shorter charging times. DC fast, charging external chargers supply. DC power directly to the battery. Some systems can charge up to about 80% in roughly 20 to 40 minutes under optimal conditions, depending on the vehicle and charger. So internally, an electric vehicle follows a clear process: store electrical energy, convert it into motion with high efficiency, recover some of that energy when slowing down, and manage everything through precise electronic control, fewer mechanical losses, more direct energy use,